But now let's continue with our keynote speakers. And the first one today will be Mr. Kallunki from Aalto University Metshovi Radio Observatory on importance of spectrum management in radio astronomy. Please, the floor is yours.
Okay, thank you. Let me share the screen. So, first of all, I would like to thank organization committee the possibility to give this talk on this very important topic of radio frequency interference. So, what can I talk today? I will start with the frequency allocation. What are the players in frequency allocations? I will talk about some general RFI issues, and I have been working past 15 years in observatory, so I have some experience on RFI issues in practice, and I will show some examples how and what kind of issues we have been faced on past years. So at the end, I will talk about shortly work done by CRAF, Committee of Radio Astronomical Frequencies. So, but let's start with the basic. You probably are familiar with this, that radio frequencies start from the 3 GHz and they are continuing up to some terahertzes. And usually radio astronomy observations are made at some tens of megahertz up to gigahertz. Also, of course, there's a higher frequency observation as well. So frequencies are generally allocated between several services, and only minor part of these frequencies are allocated to radio astronomy services or more general in scientific use. And of course, commercial users, they have, let's say, maybe bigger word on this allocation issues because they have usually much more financial power behind them. So these other frequency users are seen as a threat for us. And frequencies are allocated in many ways. They can be allocated in international level, European level, and also in national level. And we have to note that many of the radio astronomical observations which are made, they are actually not, they are made in frequencies which are not allocated to the radio astronomy services. So let's look at this issue in other point of view. This is basically the frequency allocation table from US, but situation is pretty much similar in Europe. So the different colors means different users or operators in frequency range. So what we can notice here that the blue boxes, which I have been underlined there, they are actually the allocation which are only allocated for the radio astronomy or scientific use. So we can see that that there are still quite much allocation for radio astronomy, higher frequencies up to over 30 gigahertz, but actually not many radio astronomy band in lower frequencies, which is a big issue at the moment and will be in the future as well. So this is one example of K-band allocation. This is situation in Finland. You can see in the bottom of the graph that the K-band observation are made in roughly 500 megahertz band, but the allocation, radio astronomy allocation, does not cover the whole band. So there's other services as well and on that band. So this is other major issue at radio astronomy. So, but however, the situation is still rather good. This is one example of K-band situation here in Metsahövi. I made last summer some interference gun at K-band, few azimuth direction and few elevation angle, and I couldn't see any interference at that band yet. But let's see what is situation in future. So this is basically what is the interference issues with other frequency users. So on the plot you can see that there's a radio astronomy band, and then next to that is some other service band. So there's a possibility that the interference from the band next to the can cause interference, that so-called adjacent interference. Also harmonics could be possible, which are coming from the bands which are outside of first band, some other services. And also in worst case, it can be, which shouldn't be possible, that there's some other operator also in radio astronomy band. There's International Telecommunication Union has defined the protection criteria for the radio astronomy services, that how much is allowed, or what is the power density which is allowed to be in radio astronomy service band. This is basically the screenshot from the recommendation. There's different radio astronomy bands, and they have been defined the protection criteria for each band, which is the allowed power flux density, what is the level which can be allowed to be in the radio astronomy bands. These are defined both for single dish mode and also in VLBI observation. And I have been highlighted this unit, that it's really power flux density. That's this bit problematic, that you just cannot take your spectrum analyzer, for instance, from your lab and start to do measurements, but you really need a calibrated system, and it's quite difficult to actually make proper interference measurements which fulfills these criteria, or this that you can compare that are the interference really harmful or not. So this is another example. When you are observing out of the RAS band, you have to accept that there might be some interference in your observation. This is an example of solar total flux monitoring, which is made here in Metsahövi. This is made in a geosatellite band. So we have to accept that in two times per year we have 10 days break for the observation, because then the signal is full of interference. So to conclude this section, I would like to mention that if you are detect some unexpected signals in your radio astronomical observation, it doesn't automatically mean that you are really facing the interfering signal. There might be a allow, or it should be there. It's other user which has allowed to be in that band. So this is basically simple scenario how the interference signal can goes to your observation. of course, it comes from the main beam or side lobes, some reflection. We have reflection. Luckily, the single dish or dish antenna has a rather small beam, so that works as a natural filter. And also the side lobes are negligible small. But my opinion, the major issue is this self-made interferences, which are actually coming from the devices what we are using in observatories. This is nowadays a major problem. So just summarize that there's a lot of different kind of interferent devices which are probably in observatories. There's a frequency converters, switching power supplies, relays, contactors, mobile phones. Hopefully there are flight mode, Bluetooth devices, welding machines, lamps, different kind of lamps. So testing and selecting devices is in a major role. That every device which is coming from your observatory, that they should be tested well. That are they really suitable for the radio observatories at all. So nowadays the problem is that even in the very common household, even fridge has some kind of radio transmitters nowadays. So you will face them in very common and unexpected places. So this is basically the one example of self-made interference. We had a major electricity repairing in a spring. So we had a possibility to do measurements when all the devices were switched off. And we repeated the same measurement the next day when observatory was in normal operation. Especially at high end of the frequency range, you can see that the noise floor is totally different when all the devices are switched off. You don't have to care about the lower frequencies because there are some kind of intermodulation results. So, but you have to take a look at the frequencies up to 20 megahertz. So there you can see the difference, clear difference between the self-made and self-made interference. So unfortunately, I cannot use this animation now, so I have to move this. So anyway, we have also major renovation in observatory last year. So we repair all the electricity devices, lamps, and everything. So we had to test all the devices beforehand, before the final installations were made. So this is basically one example of one of the lights we were tested, which caused, how to say, interesting interferences. And we couldn't use this at all because we didn't know that does it really have how much does it have affected the measurement. So we had to make take another lamp for this. So this measurement is made in a very simple near field probe. Okay, that does not fulfill official EMC regulation, but anyway, in this kind of measurement, you can really see the difference that is it really lamp interfere or not. And this was one example of these bad lamps. So this is another practical example. We know this very wide band and strong interference in our solar spectrometer, and and the interference were detected mostly in daytime, and after hours of investigation and Secret Service work, we found that it was the interference coming from this kind of compact fluorescent LED lamp. So, and then we opened the lamp, and there was no any kind of EMC consideration in lamp. So that was really harmful and bad, and it took weeks to find out the source of this interference. So this is another example. In our observatory area, there are other operators as well. We have no access to their premises. So, but anyway, we know this in our interference monitoring system, some very strong interference in up to 2 gigahertz, and we connected to that the microwave oven, but we couldn't find the source, and then we start to do better and better scanning, and then we found the source, and the source interference was coming in the building next to us, and they really had microwave oven, which was from the 80s, really old one, and it was a really bad interference source. So after that, they throw it in a garbage. So and after this investigation, we decided that when we have a spent observation of the geodetic observation, then those days we cannot use microwave oven at all. Another S-band issue. We had a discussion with the military forces. They started to use tactical link at S-band, and their base is located something like 30 kilometers from our observatory, and we made some kind of test session with them, and that could we see the devices in our observation, and we very clearly saw that link. And after that, we decided with a well cooperation with the military force that they promised to switch off these links when we have these S-band sessions. So far, this has been working without problems, but let's see how long it goes like that. Okay, this is one of the funny example. We have GPS receiver which caused a lot of wideband interferences, and we tried to find a solution how to prevent that. So in this case, it was quite a simple solution that we just put aluminum foil around the receiver, and that blocked all the interference totally. Okay, this is unfortunately has been a guest question for usually, but now I cannot do the guess because you cannot use the animation. But anyway, we are doing quite regularly solar radio maps at 37 gigahertz, and in some maps we noticed that kind of black hole, and that was also we spent quite many hours to find out what was this, and then we matched this that it is black hole is coming from the airplanes, which when they are passing our radio telescope beam. So, and of course this temperature of this airplane is something like 300 kelvins, and sun is at 37 gigahertz up to more than 8,000 kelvins. So that's why it's seen as a very cold region in the map. We have been managed to see similar events, let's say 5 during the past maybe 5 years. Okay, so how to prevent actually the interference in radio astronomical observation? There's of course a lot of solutions. There's an administrative solution and technical solution. Frequency allocation is a very good tool. Also protective zones around radio observatories. I mean, radio quiet zone should be defined around observatories. Also, there's of course technical solution, filtering, software solution, antenna design, shielding, and also the data processing techniques. But in my opinion, the most effective tool, in my opinion, is the attitude towards RFI. How do you act in observatory? What kind of devices you are really selecting? How do you are doing the testing, and so on. So that is the and how much you are allowed the transmitters in your observatory area. That is the most important aspect in my opinion, in this preventing of interference. So unfortunately, we have no time to go through all this technical solution, but I just mentioned these filters. Okay, filters are effective. They are common solution, but there's also minus sides on those. They can be rather expensive if they are in a endeavor that they should be working in a cold low temperatures. And then it might be a problem if you have to do you have to filter several notches. Then it could be very complicated to design such filters. Also tunable in the future because the RFI situation changing constantly. So you have to I mean prepare for future as well.
Just while I have a minute to interrupt, we have 5 minutes left, so maybe 2 minutes to finish off your slides, and then we have a few minutes for questions.
Okay, so okay, thanks. So a short introduction to the CRAF. The CRAF is basically the expert committee of radio astronomy frequencies. Host institute is the European Science Foundation. Each observatory has a one CRAF member, or not each observatory, but each country has one representative in CRAF, but usually it's from the local observatory. I'm the Finnish representative, and Ladislav is in Latvian representative. So CRAF is basically submitting input documents. They are doing compatibility studies for the frequency allocation between frequency users, and they are acting a major role in frequency business. So CRAF is doing compatibility studies, doing various input documentation, coordinate with general spectrum issues, doing public outreach, and basically CRAF is defending the radio astronomy against the other frequency users. So there's a lot of you can check basically afterwards on more actions what the CRAF actually is doing. There's a lot of contributions and compatibility studies what we are doing. Here's one example of high altitude base station compatibility studies. You can see in lower plot that this is basically the separation distance calculation, and as you can see that in this result shows that separation distance between radio astronomy observation and HIPS devices is more than 300 kilometers or 400 kilometers. CRAF handbook is available in website. You can look that's very nice book. Mention about CRAF. This is by CRAF. It's a simulation tool which is you can do various compatibility studies. It's available. It's open source software based on Python. You can find it from the GitHub. It's made by Benjamin Winkel from Max Planck Institute. But a few words about the new future and new threats. Satellite Mega-constellation is a major threat for the radio astronomy in future. Also 5G. This 5G issue is still quite unclear. We don't yet know the exact frequency band. Also the electronics. I already mentioned that electronics is getting cheaper, but less EMI consideration are taking there, so that they can be a major issue in the future. This is basically the how to say illustration of mega constellation, that what happens to radio astronomy if there's thousands of satellites around the globe. So after that, there's hardly possible to do any radio astronomy if this happens in future. But this is really whole own story on this. So this is also a few slides still. So this is basically what I want to mention, that each observatory should have some kind of interference monitoring system. This is one example. What can be noticed from there? This is next to our observatory, something 5 kilometers from us. Suddenly, one day we saw some strong interference at 1.8 gigahertz, and that was a new IMT base station. Nobody wasn't informed us, and that new base station will be located in near the observatory. But this interference monitoring system revealed that, and that's why it's very important to have it.
Okay. Thank you. I think we are almost out of time. So maybe if there is one quick question, we can go there. Okay, I see there is a question from Mr. Paco Colomer. Do you wish to read it out loud yourself, or should I?
Well, it's not really a question. It's a complementary information to what is being said about CRAF, which is a fantastic job, and is that there is in November a meeting about dark and quiet skies. Registration is free. It will happen in La Palma, but also online. And I just put in the chat the link if people want to check. There is a session on radio astronomy, and it will tackle the issues of radio interference.
Okay. Maybe short comment from one side. Jukka, thank you for perfect timing and the story about CRAF. And EVN now is not say requirement, but asking all stations to have verify monitoring on site, and probably it's next what in Urbane we have to do to make better our telescopes working and look for our site verified problems and collect all statistics about it. Yes, thanks a lot.
Okay, thank you.
Yes, thank you. This is certainly a discussion which must be continued, and I hope that even though this is a virtual edition of the conference, we can still do that in comments section and direct messaging.